Hello and welcome. I'm George, radiologist and AI researcher at TU Munich, Imperial College London, and a member of the OpenMined research team. I'd like to talk to you about our project on bringing privacy-preserving deep learning to the clinical routine. I'd like to motivate this talk by the fact that AI in medical imaging has recently shown encouraging results from multinational trials, showing that it can assist clinicians in tasks such as improved diagnosis and early detection of disease. This means that AI-driven diagnosis as a service tools are within reach and capable to, for example, counteract the lack of radiologists in disadvantaged areas where radiological expertise is cost prohibitive. However, considering the data requirements for training such algorithms and the way in which training data has so far been collected, namely accumulated centrally, we notice one big problem. Even with informed consent, accumulating and transmitting data impinges on a fundamental patient right, namely the right to be informed and in control of the storage, transmission, usage and deletion of one's personal data. Strict jurisdiction, at least in the EU, as well as fundamental ethical requirements of the medical profession, impose boundaries on such activities. However, in disadvantaged communities, patients may not be sufficiently informed or even able to demand the same measure of control over their confidential health data, which leads to a precarious state of inequality. Privacy-preserving machine learning provides solutions to bridge the gap between deriving insight from patient data while protecting it at the same time. In our recent article, we give an overview of privacy-enhancing techniques, such as federated learning, which relies on sending algorithms to where the data is instead of transmitting the data to where the algorithms are. This allows patients or hospitals to remain in full control of their health data and to enforce complex governance schemes which are crucial in the heterogeneous landscape of clinical records and medical imaging. Furthermore, encrypted computation systems allow for protecting both the data and the algorithms for theft or misuse in the setting of end-to-end encrypted services. This allows the provision of diagnosis as a service under the premise of what we call single-use accountability. That is, the notion that a good is provably used only for a singular purpose for which it was designated by its owner, for example, data only for receiving a diagnosis, but not for marketing or for research purposes. So far, privacy-preserving machine learning in medical imaging has largely remained in the proof-of-concept stage. Our mission, both at our universities and at OpenMined, is to translate these privacy-enhancing techniques into clinical routine as soon as possible. For that reason, I'm thrilled to announce the newest member in the OpenMined open source family of tools, which we call Premier. Premier, which stands for Private Medical Imaging Analysis, is a library for federated learning and encrypted inference on medical imaging data, and it was jointly developed by organizations. Our aim is to provide the tools required for performing securely aggregated federated learning in the multi-institutional medical setting, and to be able to provide the trained algorithms in an encrypted inference scenario. Premier is designed from the ground up to be cloud-ready. It builds upon the PySift and PyGrid toolchain and incorporates the current state-of-the-art in federated learning and encrypted inference, as well as including several medical imaging-specific innovations. Our design goal was for a moderately tech-savvy user to never have to perform more than 3 steps to carry out a specific task. For example, if you are a data owner wishing to offer their data for federated training, you need to do little more than to put your data in folders, run a single command line interface call, and Premier will do the rest. This includes full support for the DICOM format and all other common imaging formats, and even for mixtures thereof, such as DICOM and JPEG. Running federated learning is even easier. To configure training, all the important bits are in a single configuration file. From there, you just run train.py and wait for the model to train. We also include some pre-made scripts, for example for running hyperparameter optimization over the entire federation. From a design perspective, we chose a hub-and-spoke configuration, since recent evidence from medical imaging studies shows it to be superior in performance to serial training topologies, and also supports asynchronous training or, for example, nodes dropping out. All model aggregations in Premiere are performed with secure multi-party computation, using the newly introduced function secret sharing protocol, which offers great performance and robust security guarantees. For good measure, we also had our resident model inversion genius, Dimitri, who's also holding a talk at this conference, attack the model, but all we got was random mod noise, so it's working pretty well. Encrypted inference is just as simple. All you need to do is set up computation nodes as crypto providers and model servers, and wait for a request from the data owner. Everything is driven from the client side, including outputting the encrypted result as JSON on the client device, and everything happens under a zero-knowledge, end-to-end encrypted premise. For the last part of my talk, I'd like to briefly talk you through the case study we performed using Premiere. Despite the buzz around COVID-19, regular pneumonia kills nearly 1 million children each year, a substantial proportion of which are in low-income countries. Since chest X-rays are a mainstay of pneumonia diagnosis, we decided to train a federated remote diagnostic model which can help out in such low-income areas where radiologists are unavailable. Since hospital IT departments are not yet particularly keen on opening up their firewalls to federated learning workflows, we propose a new solution, which is the utilization of the recently introduced confidential computing nodes. They rely on memory encryption and are basically computer-wide trusted execution environments. We also benchmarked our model against a locally trained algorithm and against 2 human experts. Our model outperformed human experts on both datasets, and we found it to also perform competitively with locally trained algorithms. We also found clinicians to intuitively understand why federated learning and encryption are a good thing, and that led to high acceptance at all our institutions. We identify several key challenges for the next 5 years. Clinical data is heterogeneous and needs to be carefully curated. It's still challenging to fairly assess the contributions of the individual clients to the overall model. Encrypted computation is still expensive and in parts cannot be carried out in full precision. Federated learning has high input-output requirements, which we're looking to solve with smaller algorithms and efficient compression schemes. Let me close by saying that I'm only representing a large and diverse team of brilliant scientists and creators, without whom this project would have never happened. I'd especially like to call out and thank Alex, our lead developer, Jonathan, Andrew, Theo and Ionisio, as well as many others from all over our organizations and OpenMined. Premiere will be openly available on the OpenMined GitHub in October, and we will be hosting a first look session tomorrow, which will include a Q&A and some examples. Thank you very much for watching, and see you then.